Welcome, everyone. This is the last talk in the Rocky Mountain Rep Theory Seminar for the fall of 2021. And Haisheng Li is going to be talking about the forming vertex algebras by module and comodule actions of vertex bialgebras. Feel free to start whenever you're ready.
Okay, thank you so much. So I'm really happy to be here. So for quite a while, haven't seen everybody. So for a while now. So really so happy to have this chance to talk here. So here is the title. So basically it's about relate to vertex algebra and vertex bialgebra. Here all experts. I will just talk about ideas and some thought for that. Okay. So screen here. So I will just say, okay, for most of us working on slightly different direction. So basically just what I said here. So basically we thinking start from good vertex operator algebras, and then we study representations and then do other things. So basically from vertex operator algebra, we study other things. But for me, for quite a while, I have been interested in this question, the general question. So associate vertex algebra or their likes to algebras, so especially quantum affine algebras or Youngians. So this is the question raised by Igor Frankl and Nahuan Jin in their work after they done vertex operator representation for quantum affine algebra. In their paper, they raised the question. So that's the question. So I have been interested to try to get something done. So that's the problem here. And of course, the closely related problem is so develop quantum vertex algebra theory and then relate quantum vertex algebras to all kinds of, various algebras. So that's the problem here. So quickly mention, so for information, so of course, the first quantum vertex algebra, the notion called the deformed algebra, was due to Igor Frankl and Rashtihan, that's in 1997. And then Edinburgh Castan around 2000 and introduced the notion of quantum vertex operator algebras. The key thing here we want to mention that this is the H-adic version of that. Okay. And then, of course, 2001, so Bocher also introduced a notion for that. And then what I have been doing basically essentially follow Edinburgh Castan's work. Okay, so that, and also for completeness, also there is a work done by Gluna, how to pronounce this, Gluna and Berkeville. So it talk about HD quantum vertex algebras that's based on Bocher's work, and also partly based on Edward Frankl and Rashtihan's work for that. Okay, I want to say something about how the original idea, how I want to approach this problem. So basically from representation theory. So first we think, okay, how we associate the vertex algebras to affine algebras. And the key thing is we use representation for affine algebra, basically use so-called highest-weight models for that. More specifically, so for, let's say, untwisted affine algebra, we can talk about special highest-weight model called vacuum model. Then vacuum model has a vertex algebra structure. So, okay. Then other general highest-weight models becomes models for a vertex algebra. So that's a thing. So we also can describe this in terms of representation for that. So in terms of representation means, so you want to think, okay, if we consider classical algebra as algebra of linear operators, then here, so you think we use a generating function as an analog of linear operators, and then to generate something, okay, no matter what we get, to generate something, okay, then we'll decide what we have. So here I want to emphasize two things. So use the generating function as the main building blocks. That's one thing. Then on the other hand, we need certain tools, okay, to generate vertex algebra and subject vertex algebra like structure. So that's it. Okay. So that's the approach. Basically, try to from this side, not just to say, okay, we just assume a certain type of vertex algebra structure. No, so basically we want to start from some concrete object generating function. Then let's try to generate something. What do we get? Then study the structure. So that's the idea. Okay. And so this is the approach we are taking here in the whole thing. So I mentioned that use the generating function as the building blocks. So for this part, basically, we don't have much choice. Usually given an algebra, and we know roughly we have the basis generators and we form generating function. You could slightly change the generating function, but essentially same thing. So for those building blocks, we cannot do much about that. So let me just mention the quick idea here. So suppose W is just a general vector space, of course, and we consider so-called the vertex operator, just a formal series, or called quantum field or whatever. And that's the main object that then you want to generate. Generate here means in physics or in classical case, when we say generate, we use whenever we consider operators. So we consider composition. And in physics, in physics, if you consider vertex operators, when we say generate, we can consider so-called operator product expansion. That relates our weak associativity. Okay. But here I just want to emphasize, essentially, we have this composition, and also formally we have this substitution, replace x1 by x plus z translation. That we want to emphasize that. Okay. And the key thing is, if we just use this format, okay, and a lot of times so we get something, but we don't get what we need. So then, especially for quantum affine algebras, then we think about maybe there are other ways to generate. So here we use this substitution x1 equals x plus z. So maybe we can have others. So that's an idea. So just to mention that, so actually a long time ago, I guess a lot of people realized, especially in one of Botcher's paper, realized that formal group law implicitly plays very important role in the notion of vertex algebras. So if we look at the weak associativity x1 in the form, replace x1 by x2 plus z or just x plus z, and there we have a formal series. This is f for two variables. That one happens to be a formal group law. So that is the one-dimensional additive formal group law for that. So that means the physics usual OPE use this formal group law. Okay. The next one then, so okay, realize, okay, maybe we can generate this part, not use the formal group law, but in like for group, you can talk about group, and we also can talk about the G set, group acting on set. You have the action, right? It's not algebra, but you use the G set, you get a model, not algebra. So here, this is the idea, and then you try to see, and indeed, so we consider more general substitution here. So replace x1 by this is phi xz, and in the formal law, just x plus y, but here is a formal series. And naturally, so we will need this exactly like G action, group action. And in the last, in this equation, the red one here, one like identity action, one like associativity. Okay, so that's what we call associate for that formal group law. So you just for every associate, and we can form we can introduce a theory of a 5-coordinate model for vertex algebra. Okay. So for this is 5, that's the definition, but it happens to just relate to a Virasoro or Witt algebra. So if we pick up arbitrary formal Lorentz series Px, you consider this a formal exponential for that. So we know that if you consider Px just monomial, just x to n, xn d of times d dx, that's related to Virasoro L, what that's, if you shift that L, what that's L n minus 1 plus 1 will shift, right? But that's a Witt algebra. So for that. So in this case, for every formal Lorentz series Px, you define your phi this way. So that gives you associate. And then immediately you have 2 particular cases. One is, of course, the formal group law. And you take Px to be 1. Another is if you take Px to be x, and you get this x times e to z. So actually, this is the main reason for us to talk about this. This is exponential. So exponential basically, you're thinking about exponential function basically relate to additive structure with multiplicative structure. That's the thing. In our usual weak associativity or OPE, we use additive law. Okay, but the thing is when we study quantum affine algebras, and when you talk about that breeding, it involves the so-called trigonometric quantum Yang-Baxter operator that is not additive, but is multiplicative. So that's why you want to think about some way to relate trigonometric rational quantum Yang-Baxter operators with rational quantum Yang-Baxter operator. So that's the idea, okay? And then here, as I mentioned before, so basically for every coordinate, and you can develop a theory of 5-coordinate V model for vertex algebra for that. So of course, this associativity, with associativity just using the 5-coordinate. So that's the idea. Okay, so that's the roughly, so what we have been doing. So here is the general layout. So why we talk about no-local vertex algebras or quantum vertex algebras or H-adic, why we do that. So the layout is here. So first, we have vertex algebras over C, that's the usual algebra. And then horizontally, so still over C, but we can consider generalization, horizontal generalization. Okay, deform certain things, okay, change some things, we get quantum vertex algebras or weak quantum vertex algebras, that side. So we will mention a little bit later. And then vertically go to the left side, and you consider formal deformation. With the H, just the formal variable, you formally deform that, you get quantum VOA. That is the adding of a custom notion. If you consider classical limit, you go back to vertex algebra. But here on the right-hand side, and we have weaker or quantum vertex algebras, you consider H-adic version, we get H-adic quantum vertex algebra. The difference is here, adding of custom VOA, just the special H-adic quantum vertex algebra. So let's just say on the left side, adding of a custom quantum vertex algebra, there are classical limits, just the vertex algebra. On the right side, for a general H-adic quantum vertex algebra, and the classical limit is a quantum vertex algebra. So actually, in adding of a custom notion, and they already mentioned that they talk about deformation vertex algebra, but also they mentioned you could talk about deformation of like vertex superalgebra. Okay, that also means you can go further, maybe color algebra, right? So that's so quantum vertex algebra over C basically in that sense. So you see this whole picture. Okay. So I believe this up to H-additive quantum vertex algebra. So basically, for all those those algebras we are interested in, so this is big enough. And okay, some notes. The first one I already mentioned that the weak quantum vertex algebra, just the generation of the vertex algebra. Basically, you can consider vertex super algebra and the color algebra, whatever. Okay. And adding of a custom notion, I already mentioned that just formal H deformation vertex algebras. And as for H quantum vertex algebra, I mentioned that classical limit, not vertex algebra, but quantum vertex algebra. Indeed, so what so in the past we can do is we can associate H-additive quantum vertex algebras to double Youngin. For double Youngin SL2 at the generic level, that can be done. Okay. And also for quantum F1 algebra, and some part down here, I say conceptually, exactly in that picture, means start from quantum F1 algebra and you consider a general highest weak model, you consider dream field generating function, and then use this kind of format, and indeed they generate weak quantum vertex algebra, and then you have that. So this is a rough picture, so that's why I say conceptually. But of course, the main problem, so we do want to characterize those desired quantum vertex algebras, or we want to say we construct them explicitly by using certain classical algebra, certain classical data to get the vector space explicitly. Okay, so that's the idea. But for that part, actually, we had an issue. So usually, whenever you have Lie algebra, something is a little bit easier. We could use universal invariant algebra, something we know already. But in general, in this case, conceptually, we get some quantum vertex algebra, but it's hard to describe it. First, will involve PBW basis stuff. So we will need to discuss, study new algebra for that. Okay, so then that's why we move to, try to get a help from hopeful algebra. In hopeful algebra, indeed, so there are a lot of tools they use, like smash product, they have Hasenberg double, dream field double, also dream field twist. They use them as if they are effective tools to construct hopeful algebras or quantum groups. So that's the thing. So then naturally we think, okay, maybe this is something we can do to get and develop certain vertex analogs of those classical things. Then we can use them and to construct a desired quantum vertex algebra. So that's the idea. Okay. So for instance, if you consider symmetric product, basically, or a twist, usually when you say twist, you already have a classical structure or vector space at least. Then on that same space, you twist the structure, you get something. So the space is clear at that time. So that's why, okay? So at least you have a very explicit space. So that's why, okay? Okay, so that's the introduction, but the whole talk, not the whole talk, at the end, there's mainly based on the joint work with Na Huanjing and Fei Kong and also Xiaobin Tan at the end, right? So I will mention that later. Okay, so that is a kind of introduction just to tell you what we have been doing, why we do this. So some motivation. Okay, all expert, I will just quickly go. Just mention that for vertex algebras, we emphasize among the main axioms, we could commutativity, and also we have a associativity, commutativity, associativity. So that means we think vertex algebras are analogs of primitive sortive algebras for that. And then if we have that one, if we want to talk about more general quantum vertex algebras, just like for quantum groups stuff, so we need to relax something. So, or you still consider this in a certain category. So here we still think about we should do this inside the category of associative algebra. So non-local vertex algebra is simply just analog of associative, not in general, not commutative, just associative algebra. So that means only associativity, but no commutativity. So that is the bigger category. Inside there, we play a game. Then we properly add a little bit commutativity. So that's the point. Okay. So I already mentioned that the notion of non-local vertex algebra is defined by almost the same axiom, except the weaker commutativity for that. So here I mentioned that for this part, non-local vertex algebra is the same thing as a field algebra introduced by Bacalov and Kash, and also at that time also called the axiomatic G1 vertex algebra. For my work, actually motivated by Borcher's notion of G vertex algebra. That's more general, higher dimension stuff. Okay. Okay. For weak quantum vertex algebra, so I already mentioned that the generalization for super algebra. So let's quickly go through this. First, we have the weak commutativity and weak sortivity, and then only thing is this is the weak, or what you call S locality. This is notion due to Eddington-Custom. Okay, simply you just look at the bottom here. For two associated vertex operators, when you commute, on the right side is not necessarily YV, X, YU. Okay, so on this side is a finite sum. And the coefficients are not just a constant, but instead a function for that. Okay, so that's the definition for this one. So something a little bit uncertain because they're just existent on the right side. But that is good enough when you do some theory. But okay, for quantum value algebra without a weak, so this is basically is the kind of directly we can see this from Eddington-Custom notion of quantum versus operator algebra. For Eddington-Custom notion, I say because it's H-adic. And here you just consider, okay, without H-adic, you just directly get the axis. Okay, and for that. So one thing quick, one main thing is the so-called unitary rational quantum Young-Box operator. That one controls the S locality. When you switch them, so basically we do see a map or linear operator from U tensor V to the other place. When we say exist, it means a linear map. Okay, so that linear map is given by this unitary rational quantum Young-Box operator for that. Okay, so then satisfy natural compatibility condition for that. Okay? So I just quickly move that part. So what I want to say is we have this weak quantum vertex algebra. So you just say, okay, sometimes you want to generate something, but you don't want to make it too wide. So just like, let's say if you study algebra, if you just say social algebra is it's hard to say it's too wide, but okay. But if you even just forget about social algebra, there is too wide. If it's too wide, of course, very, very general, everything fits that pattern. But the problem is too wide. It's out of control. We cannot study. Here we want to say, okay, weak quantum vertex algebra is not too wide. And if you look at the axiom, you still have, we can have certain like Jacobian identity, right? So the key thing is for weak quantum vertex algebra, you can develop the theory in a similar way, just like the usual vertex algebra. Okay, and that's one direction. The other direction, not too wide and not enough. You want to say this is large enough. Basically, we have something in mind, and we want to make sure, okay, and we can associate quantum vertex algebra to any various algebras we are interested. So that's the thing. So two directions, not too wide, but we want to make sure it's not too narrow. So we definitely, so we can do something for that. Okay, so that's the thing. I do believe with this notion of quantum vertex algebra together with H-adic analog, and also we need the quasi-model and the phi-coordinate quasi-model. Those theory enough to basically associate the quantum vertex algebras to, I cannot say all algebras, but those we are interested in. Okay, so it depends which algebra, what you want to do. Okay, now I mean got something detailed for the classical algebra. So I will just quickly move. Okay, for co-algebra, of course, two structure, co-multiplication, co-unit, and then the associative side. Okay, let's test this one. Okay, key thing is here we want bialgebra. So bialgebra, so bi means two things. We have a associative algebra structure. On the other hand, we have a co-algebra structure on the same space. And the co-algebra structures, the two maps, are associative algebra morphism. Just that. And also equivalently, as we believe the usual multiplication and the unit map, so are co-algebra morphism also. That's it. And a quick example, of course, for co-algebra, bialgebra, so group algebra is one. Another one, of course, the universal invariant algebra. And then the tensor product. We all know that these basically roughly give you all those good hopeful algebras, right? Certain co-commutative and pointed or something, so they give that. Okay, and then let's try to go further, relate this to a vertex algebra stuff. So here we have differential bialgebra here. So first, differential algebra here means, just the terminology, means associative algebra with identity and also with one derivation. And differential bialgebra, of course, so we add more. So it's a bialgebra with a derivation satisfy this natural property. So that means the code structure also differential algebra morphism for that. Okay. And then, so we consider, you see, usually we just have the classical example. Now you want to get the vertex stuff. So here example one, and if we G is a Lie algebra, then we consider the in the loop Lie algebra, we consider the negative part. Then we consider the universal invariant algebra. That one, naturally, we have a differential derivation, just a d over dt. So this is a differential bialgebra. And another one related to lattice vertex algebra. And suppose L is a billion group. And on one hand, we have group algebra. And then on the other hand, we have this, we want to get Haisheng algebra. So, but here, we don't assume we have a bilinear form yet, but we get H complexification of L. We get billion Lie algebra, and then just like the first example, we have the universal invariant algebra, that's symmetric algebra. Then tensor with the loop algebra, I mean the group algebra. So naturally, that is a bialgebra, actually also a hope algebra. And also we have a derivation. Okay. Okay. So because for a lattice vertex algebra, we have this, so I just move on for that. So this is a very simple vertex bialgebra for that. So two parts, and the group algebra together with this symmetric algebra for that. And then, of course, always here's the buttress construction vertex algebra. We know that. So just quickly mention if A is a commutative social algebra with derivation, and then that is the Boucher's construction. Then, okay, and then move on. The relatively new thing is about vertex bialgebra. Bi here again, so we want to have double structure. One is a non-local vertex algebra, also a co-algebra actually. Here is one definition. We will make a remark later, but let's say non-local vertex bialgebra in this sense means a non-local vertex algebra. And this is a full non-local vertex algebra. On the other hand, we have a classical co-algebra structure. I want to say just classical. And then the classical co-structures, maps, are non-local vertex algebra morphisms. Okay. So here, just the standard classical co-algebra structure here. So some examples. First, if A is a differential bialgebra, then use the Boucher's construction, we have a vertex algebra. And also at the same time, we have a co-algebra structure. Then that is a bialgebra, vertex bialgebra. And another one, of course, we mentioned the example from a Lie algebra, then we consider the negative part of the loop Lie algebra, then consider universal invariant algebra, and use Boucher's construction again, but this time you get a non-local vertex algebra, but this time is a non-local vertex bialgebra. That is also simple. Another one is what we get as BL from a Billing group of L, the tensor part. So that because this time is a commutative, this time is a vertex bialgebra. Okay. Actually, in this talk, and we will use this vertex bialgebra a lot. So that will be the main tool we are going to use because this is related to lattice. Okay. Here, this is a quick remark because we mentioned a vertex bialgebra, the two structures here. We're thinking about vertex analog here. But in the previous definition, we only used a classical co-algebra structure. Here I mentioned that vertex operator co-algebra was studied by Hubert. So the first two papers there. So basically just a co-algebra structure is just to consider do of vertex operator algebra, purely just a do. And when I was preparing the lecture, I also realized Florence also had this interesting paper. I didn't have time to read all the detail, but I found that one. So for a while, I didn't check this one, you can see. I done this part, some part a long time ago, 2007, but and then pick up again for certain purpose. Okay, so what I want to say is, for vertex operator co-algebra, so only co-algebra structure you consider do. So here, actually, lots of questions, to be answered here. So here, one thing is, let me mention this. In the notion of vertex co-algebra, we have vertex co-multiplication. So that means from V to this purple one, if we want to think about bi, if we want to put vertex co-algebra and vertex algebra together, if we want to get a bi stuff, okay, then we will think, okay, can we consider vertex co-multiplication as homomorphism of vertex algebras? Yeah, that's the next question, will be that one here. Okay. For this set in purple, actually, how can you give this space a reasonable vertex algebra structure, make this as a homomorphism, kind of minimal homomorphism? Okay, so that's the question. The next here thing. Okay, so can we make a vertex co-multiplication of vertex algebra morphism? Because we want to think about bi algebra. Okay, if we use that to do, seems pretty tough actually. So for vertex algebra, but still a question, okay, you can think of. But sometimes we can relax a little bit. So here, as we mentioned in the definition of vertex bialgebra, we only use the classical coalgebra structure, the simplest one, constant. But for general, if you go a little bit further, okay, not the very, very general vertex coalgebra structure, maybe kind of restricted a little bit. And then we can consider kind of vertex bialgebra, the more general, okay? But it's not a classical coalgebra structure. One possibility could be this, that this is co-multiplication map. This is vertex in the purple for that. So not V tensor V like the before, but here is just a tensor with Lorentz polynomial ring, the other direction. And in the top there, that is the Lorentz series in x to -1, because that's the duality, the do. So basically you have left model, right model, you have this do stuff. That's why you get a negative power. But that's kind of related to so-called left model, right model for vertex algebra. I also called models at infinity. So maybe that's related to that, but it's still a question here, okay? So something for us to think about this. So of course, also behind this depends so what we have in mind. So not just a notion, but so what do we want to do? Use this notion to do something concrete, practical. Maybe construct a new example of vertex algebras or something like that. Okay, so that's still open area actually. That's the question here. Okay, and indeed I mentioned this kind of idea to some students in China about this, but still this is still just an open question as to how you do this. So not just a concept. Really, even you have the concept, you go to the result, but you still want to get application. Can you apply this to something concrete, okay, to get a concrete result? Okay, so another issue related to smash product. So suppose B is a vertex bialgebra, non-local vertex bialgebra. So here we consider model non-local vertex algebra. So two things. It's a non-local vertex algebra, also a B model for that. But the only thing is the requirement. So the key thing is if you have a non-local vertex algebra, so it acts on itself. On the other hand, the B model means B also acting on there. So two actions, compatibility, that's one thing. So here's three conditions here. The blue one, so we'll mention that the blue one is a technical condition. So we'll mention that blue one, actually, maybe just write down this. The first one is a technical condition also for the third one, okay? Because you want to make sure the right side makes sense. So here is the V tensor, this Lorentz series field. This tensor means finite sum. If we don't have this finite sum, the third equation, the third relation, we cannot make it make sense for that. So that's the thing. Second one, not new, the same as the classical theory. Simply means, so you have a one-dimensional model for that. Okay. For the third condition, simply just the vertex algebra analog for the classical one. So, okay, so that's the model vertex algebra. And then the smash product. So that means you have a vertex, non-local vertex bialgebra B, and on the other hand, you have a B model non-local vertex algebra, and then you form this smash product. And the vector space is simply just the tensor product space. And then the action, pretty natural for that. So for this one, you think about of course, in the classical, you either think about group action, diagonal action, or if you think about Lie algebra, right? So that's also we call diagonal action. So that's it. And a lattice vertex algebra quickly, things all expert, I just pass. Okay. For lattice, I just want to say that for lattice algebra, we need this twisted group algebra L for L. Okay. And on the other hand, so we have the Haisheng algebra stuff. So like before, so here we use at the bottom, the red one, BL epsilon. So this one, because the twist, actually this time is not a bialgebra, as this is just a differential algebra. So this is a non-local vertex algebra also, because you have derivation. Okay, okay, let's go on. For lattice vertex algebra, we know that. So the symmetric algebra tensor this twisted group algebra. And okay, let me just give you the key point for that. For vertex algebra, we all know this. For every lattice element alpha, and E alpha in the twisted group algebra, and the corresponding vertex operator expression is this. I want to emphasize we have E minus E plus, we have E sub alpha left multiplication. On the other hand, we have X alpha to 0 for that. I purposely use different color. The first two part I use red, and the second I use blue. So the thing is, we know multiplication is so-called the creation operator, and alpha 0 that's related to derivation, that's annihilation operator, and also for plus use annihilation operator also. So red part is about creation operator, and the blue part is about annihilation. Okay, so basically two parts for that. Okay, then we can just separate them to study this. So we recall that BL first, without using the twist. So we have that versus bialgebra, it's a commutative, co-commutative, everything. On the other hand, we have BL epsilon, because we have the twisted part is non-commutative anymore, but it's a differential algebra, also a non-local vertex algebra for that. So they share the same space anyway. Okay, small change. Here, what we get is here. So for BL epsilon, it's a differential algebra. Naturally, it's a non-local vertex algebra by Botch's construction. Very interesting. So use the Botch's construction. If you work out the vertex operator explicitly, what we get is this. So for E alpha, the corresponding vertex operator in Botch's construction actually has this form. Just the red part, the creation operator form. Okay, the definition use just the multiplication and the derivative. But if you work out the form, look at this one. How about the annihilation part? The annihilation part gives module structure. So this is, on the other hand, for this BL epsilon, that guy is a BL module structure. So for that one, the corresponding vertex operator is given by the annihilation operator, the blue one. So for the other half. So the other half, so give a model structure, and then this time BL epsilon, so becomes the B model non-local vertex algebra. So originally we have vertex algebra, lattice. Now we can basically break them down into two parts. Very interesting two parts here. That's it. Okay, and also for BL, we have the co-algebra structure for that. And so for BL epsilon, of course, we mentioned that they share the same space as BL. Then we may think, okay, we have this co-map delta from BL to that. Okay, so now, so what we have is actually this one. So we have BL on the right side. or you also can consider smash product on the right side. Smash product, exactly with this as the underlying space. So this result says, okay, on the right side, if you consider this vertex structure, the smash product structure, so BL, and through this co-map here, and the image is a subalgebra. Actually, that subalgebra is isomorphous to lattice vertex algebra VL. This is VL exactly is the subalgebra in the smash product, exactly is the diagonal. Okay, so that's the interesting part for that. Okay, then the relative new thing is the joint work here. So we want to do further. So to consider deformation further. Okay, before we mentioned that basically lecture model vertex algebra structure. Now there's of course, because in the classical theory, we also have right co-model vertex co-algebra structure. So here, suppose H is a non-local vertex bialgebra. And here we can talk about right co-model non-local vertex algebra. Two parts. You have a non-local vertex algebra, and which is also a right H co-model. And just the key thing is right co-model. So just the structure is a map from V to V tensor H. As a co-model satisfy the condition, the equation 1, 2 part, but we require this guy is a homomorphism of non-local vertex algebra. More or less like the definition of vertex bialgebra stuff. It is a homomorphism, but this time the co-model structure is a homomorphism vertex algebra. Okay, so that's the definition of this one. Okay, then so what I'll do is relate to the title. We want to use combine left model structure together with the right model structure, and to deform the vertex algebra structure. If we want to use the two, of course, we need compatibility. So we need to assume both of them compatible in certain way. So that's it. So suppose H is a non-local vertex bialgebra, and V is a non-local vertex algebra. And suppose on V, so we have an H model. This is a left model non-local vertex algebra. And this is the notation, the model map. On the other hand, suppose we have a right co-model structure for that. Then compatibility, the two compatibility means this is row map. We consider domain and codomain as models for H, okay? Because V already, the domain V already a model for H. But for the right side, so our H only act on the first factor. Okay, so just that. Okay, so that's the definition. Compatibility just means that is also a H model homomorphism. And then that's the result. If we have compatible left model structure and right co-model structure on a non-local vertex algebra, and then we can deform the original non-local vertex algebra structure. Key thing is the vertex algebra map. So the key thing is definition here in the right side. They use, you see that basically use the co-model structure. This is row send A, two part, one is in V, one in H. So we know that on V, we have two actions. One is V acting on V, another is this H acting on V. So we use two parts. H acting on V first, then V acting on V second. But we use the same X here, the same variable X. So to make sure this makes sense, that's why we define left model action. We require that the image inside the V tensor, the Lorentz series. So that's why. And in this way, this will give you a structure of non-local vertex algebra. So on this same space, and you can define this new vertex operator map. So you have a new non-local vertex algebra. So that's the idea. Okay. So we use the two action on a non-local vertex algebra, not bialgebra action, left and right. And then, so we could get in special case, we could get a quantum vertex algebra. So here, so we need to assume, I will say first and then mention why implicitly. So H is here we assume is a commutative and co-commutative vertex bialgebra, very strong commutative and co-commutative vertex algebra. And then let V, suppose V is a vertex algebra. And suppose here you have a right H comodule vertex algebra structure. And of course, you also have a compatible Leclerc model vertex algebra structure. And then we want to say actually that deformed vertex algebra is a quantum vertex algebra. The key thing is the Young quantum operator is given explicitly. That's the thing. Yeah. Okay. So need compatibility. That's like before. Here, the given non-local vertex algebra V is a vertex algebra this time. And also for non-local vertex algebra is assumed to be commutative and co-commutative. We need to use both of them. Now I want to say why this. So this reminded me something. If you think about deformation, you want to get explicit formula, deform algebra. Okay, you go back to the usual quantum deformation for associative algebra. How do you do it? So usually you always start with a commutative derivation. It's like commutative Lie algebra, you can do that. But as far as I know, right now, you can. It's hard to get very explicit deformation. Even in conservative, the existence is just existence here. In general, you can have certain deformation existence. But explicitly, it's hard. As far as I know, only they have for certain, for non-commutative case, they only can do like for two-dimensional non-commutative Lie algebra. And for that one, they can do the deformation. But in general, if you don't have commutativity, it's hard to get explicit deformation formula. Okay, here roughly very explicit in some things. So that's why, in general, it's not easy to get explicit deformation. So here, that's why, in this case, in the whole proof, you see that we'll need the commutativity and the co-commutativity for that to get this one. Okay, so that's the result here. Okay, and the example quickly, so a few minutes. Go back to lattice, we know that already. Okay, and then just back two things on VL, and we want on one hand we have VL versus bialgebra, commutative and co-commutative, not problem. VL is a versus algebra, and that's the comodule. Actually, this comodule map exactly is we mentioned that BL, VL essentially the same space. Okay, just a different structure, same space. And if we think about the original, the classical the co-map delta, that exactly is this row. That's delta become row. This row exactly gives us a right BL comodule versus algebra structure on BL. Okay, exactly that's one here. That's the first one. So this, in this way, we have canonical right BL comodule versus algebra structure. Okay. On the other hand, we can construct a family of left model versus algebra structure. On the other hand, for that part, it's sort of using I think Castan's so-called pseudo derivation, related to pseudo derivation here. For any Gadan element, for any fx that Lorentz series, and we consider this is related to the pseudo derivation for that. Okay, so basically the formal series, power series, an just the mode for the vertex operator associated to a. That's the one n greater equal 0, just the annihilation operator for that. And then, so for any linear map F, send the Gadam to Gadam tensor this, okay, constant 0, because we want to consider exponential to make sure exponential exists. So that's the reason. Then we have a BL model structure on VL. This is uniquely determined by generator E to alpha, because for BL, it's a commutative, it's a differential algebra, basically as a differential algebra generated by the group algebra. So this B model structure is uniquely determined by this condition, the blue one. So if we in the power, if you think it's pseudo derivation, exponential is like a pseudo endomorphism or pseudo automorphism. Okay. So then furthermore, so BL becomes the BL model versus algebra. So you have a family of BL model structure paired parameterized by this function F for that. Because of this, and then once we are given an arbitrary F, and we can use this guy and we can get a deformation or quantum vertex algebra structure on VL. Okay, so such that the corresponding vertex operator is given by the two equations in blue. That's for that. Okay, so that's the main result for that paper. So just a final remark quickly. So originally, I sort of planned to talk about a new thing, but unfortunately we didn't finish everything. So that's why I still go back to the older one. But I'll just tell you what I'm doing. So basically, so what I was doing is we are doing consider H-additive version. Key thing is consider H-additive version of this. So we'll consider H-additive quantum vertex algebras, and then you term of phi-coordinate model. Key thing is we want to associate the quantum vertex algebra to quantum affine algebra ADE type, relate to lattice. So the main ingredient and the formal deformation, not deformation, just expansion basically, H-additive vertex algebra for VL, and then for BL, that's H-additive vertex bialgebra. Then for that F, and for that F here, so we will consider, we call eta, some linear functions from Gadam to Gadam, but here involves H. This one actually comes from relate to definition quantum affine algebra, relate to the breeding, use the breeding to define this, okay? And then, so we use that format, and then on the H-additive vertex algebra, we use the previous result, and we can get H-additive quantum vertex algebra. On the other hand, so this is not related to quantum affine algebra yet. So what we do is, okay, then quantum algebra, if you consider a high-weight model for quantum affine algebra, actually relate to phi-coordinate model for this H-additive quantum vertex algebra. So here, so we have to use deformation of twisted VL model. That's also related to a phi-coordinate VL model. Okay, the thing is, we get quantum vertex algebras. They are not models for quantum affine algebra. So that's a different thing. So the whole picture here is we get H-additive quantum vertex algebra, but for the twist affine quantum affine algebra, the highest weight model for the twist quantum affine algebra actually is a phi-coordinate model for the H-additive quantum vertex algebra. One simple analog is this. we mentioned that if we start from untwisted affine algebra, we get vertex algebra. Vertex algebra also vacuum models for untwisted affine algebra. But if we start with highest weight model for twisted affine algebra, we can use a similar pattern to generate vertex algebra. But the vertex algebra is not a model for the twisted algebra. Twisted affine algebra is a model still for untwisted algebra. So here the same thing. Even you start with a quantum affine algebra with a model, you get quantum vertex algebra, but which is not a model for quantum affine algebra. Okay, so the philosophy, the spirit is the same thing. Okay, okay. Here I think that's where actually that's the end of my talk actually. So very rough, give you a very rough idea. Okay, okay. I will just stop here.
Thank you so much. Thank you very much.
Thank you. Thank you.
Yeah, let me stop the recording before we move on to questions.